Okay, so now what we're going to do is we're going to take this approximation to the second derivative and show how from this approximation we can create a system of linear equations that in principle we can solve, and the solution of that system of linear equations is going to approximate the solution to this differential equation right here. So here's what we're going to do. We're going to begin by dividing our interval from 0 to 1 into n equal length subintervals. Okay, I'm going to illustrate this with n is equal to 5. So I'm going to divide this into 5 equal length subintervals. So something like this. And all of these points then are equally spaced. So we're going to call this first point here x0. This is going to be x1, x2, x3, x4, and the last one is going to be x sub n, which in this case n is equal to 5. And now here's what we're going to do. At each one of these points, we're going to define u sub k to be equal to the value of the solution at that point. So we're going to look at the solution here. It's going to be u0. The solution here is u1, u2, u3, u4, and u5. And what we want to do is come up with an equation that lets us approximate what each one of these values are. And so the output of this algorithm is going to be the approximation of u at each one of these points. So we will know approximately what u is at each one of these points. And the idea is that we take more and more subintervals, those approximations approach the actual value of the solution. Okay, so two things to note out. In this case, we have these boundary conditions. U of 0 is equal to 0. So that's equal to 0. And u of 1 is equal to 0. So it means, in this case, u sub 5 is equal to 0. So in this setup, we have initially 6 unknowns, u0 through u5, but the boundary conditions reduces 2 of those unknowns. So we have u0 equals 0 and u5 is equal to 0. And so now we have n minus 1 unknowns. And in general, this is what's going to happen. We're going to have n minus 1 unknowns, and so we're all going to have to get n minus 1 equations. So how can we get the equations? Well, now we're going to start looking at our differential equation and this approximation right here. So what this says, it says that at every point, the minus u, the second derivative of u evaluated at x times minus 1 is equal to f evaluated at x. So in particular, it holds for x1. Let's just look at x1 as a demonstration here. So f of x1 is equal to minus u double prime of x1, if u is a solution. Okay, and now what we're going to do is the following. We're going to use this difference right here. And we're going to let, for this problem, h is going to be the length of these intervals here, the length of those intervals there. So that's just going to be the total length of the interval, which is 1 in this case, divided by the number of subintervals, which is n. Okay, so what we're going to have is this is going to be minus, for this minus sign here, u of x1 plus h. But x1 plus h is x2. So we're going to have u of x2. So the x1 plus h corresponds to u of x2. Okay, but u of x2 is just u2. That's what this notation means here. So we're going to have u2. Then it's going to be minus 2 times u of x1. But u of x1 is just u1. And then according to that formula, we're going to have plus u of x1 minus h. x1 minus h is x naught, and so we're going to have u naught here. Of course, in this particular problem, we know that u naught is equal to 0, so in this case for x1 we don't have to include it, but I'm just putting it here now to make it look like that formula over there. Okay, and we're also going to define another notation here where f sub k is equal to f of xk. And this is not an exact equality, this is an approximate equality. And this is equal to f1. Okay, so what we're going to do then, this right here is an approximate system of, or it gives an approximate equation that relates f1 with u1, u0, and u2. What we're going to do is just solve the exact equation. We're going to solve this equation like this. There's going to be more equations as well, and the solution to that system of equations is going to give us an approximate solution to this equation in the way that I just described. So what we're going to do then, instead of looking at that, the differential equation, at x1, I'm just rewriting what I had there before. We're going to have minus u2 minus 2 u1 minus u0 divided by h squared, and this is equal to f1. Okay, now this is only in terms of the differential equation. If u satisfies the differential equation, this is only an approximate inequality. So I'm not claiming that these things are true. I'm just replacing an approximate inequality, or sorry, an approximate equality with an exact equality, and then I'm going to solve that equation. And so the solution to that approximate, the exact solution to that equation will give us the approximation to the solution to the PDE here. Now, one thing that turns out to be a little bit helpful is we want the h squared over there. So we're going to rewrite this even a little bit more and get minus u2 minus 2 u1 plus u0 is equal to h squared times f1. Okay, but we're going to have something similar is going to be true at u of x2. So minus u double prime evaluated at x2 should be equal to f2. And if we put x here equaling to x2, well, x2 plus h is going to be x3. x2 minus h is going to be x2. And so what we're going to have is the following: minus u3 minus 2 u2 plus u1 is equal to h squared f2. And then we're going to have for x3, we're going to have minus u4 minus 2 u3 plus u2, and this is going to be equal to h squared times f3. And then finally for u4, we're going to have minus u5 minus 2 u4 plus u3 is equal to h squared times f4. Okay, now up here for this equation, u0 is equal to 0, so we're going to get rid of it. And down here, u5 is equal to 0, so we're going to get rid of it as well. Now what we want to do is we want to write this in matrix vector form. We want to write this as a matrix vector equation. Okay, so in other words, we're going to have our unknowns, u1, u2, u3, u4, and this is going to be equal to h squared times our f vector, f1, f2, f3, f4. And now what are we going to get over here? Okay, this is going to be the matrix, and it's going to be the coefficients on, it's the matrix of coefficients. So it's the coefficients on the u's over there. So it's the number of equations is 4. Each row corresponds to the equation. So the top row is going to correspond to the first equation, and so on and so forth. And each column corresponds to the different number of variables. So there are 4 equations, 4 variables. This will be a 4 by 4 matrix. So the top row, to figure out what the entries in this top row need to be, I need to look to see what the corresponding coefficients in the first equation are on u1 through u4. Okay, so this right here is going to be the coefficient on u1 in the first equation. So if I look up here and distribute this minus sign, I see that the coefficient on u1 in the first equation is 2. This entry is going to be the coefficient of u2 on the first equation, which I see is equal to minus 1. This is going to be the coefficient on u3 in the first equation, which is 0, and similarly for u4. Now for the second equation, this entry is going to be the coefficient of u1 in the second equation, which is minus 1. This is the coefficient of u2 in the second equation, which is 2. This is the coefficient of u3 in the second equation, which is minus 1. And this is the coefficient of u4 in the second equation, which is 0. Okay, for the third equation, 0 is going to be, or sorry, this is the coefficient for u1 in the third equation. u1 doesn't appear, so that's 0. This is the coefficient on u2, which is minus 1. This is the coefficient of u3 in the second equation, which is 2. This is the coefficient of u4 in the second equation, which is minus 1. And down here, finally, this is the equation, this is the coefficient on u1 in the fourth equation, which is 0. The coefficient of u2 in the fourth equation is 0. The coefficient of u3 in the fourth equation is minus 1. And the coefficient of u4 in the fourth equation is equal to 2. And so notice it's a little bit difficult to see the way that I have it written here. Things are a little squashed together. But this matrix has a very nice structure. The diagonal has 2's on it. The diagonal above the diagonal have minus 1's on it, and the diagonal below the diagonal has minus 1's on it as well. So a matrix like this is called tridiagonal, meaning a diagonal matrix is a matrix that only has a non-zero diagonal, and a tridiagonal means that the diagonal above the diagonal and the diagonal below the diagonal are equal to minus 1. You saw a matrix like this on your week 1 homework. Okay, so this is the sort of explicit case in the case of n is equal to 5. But for a general n, the formula is going to be roughly the same. Well, the formula is going to be the same. For a general n, n equals 3, 4, 5, 6, 7, whatever. For each k, we're going to have the following equation. We're going to have minus u k plus 1 minus 2 uk plus uk is equal to h squared times fk, and this is going to be for k equals 1 up to n minus 1. So we have n minus 1 equations. Now, maybe one thing to point out here is that when k is equal, this should be minus 1. When k is equal to 1, uk minus 1 is u0, which is going to be equal to 0 if these are our boundary conditions. And when k is equal to n minus 1, uk plus 1 is going to be equal to u of 1, or u sub n, which is also 0 in these boundary conditions. But for different but this is true no matter what the boundary conditions are. Once we apply the boundary conditions, we can get special formulas for k is equal, for the k is equal to 1 and k is equal to n minus 1 case. In all of these, no matter what n is, it's going to result, the matrix of coefficients is going to be a matrix where we have 2's on the main diagonal, we have minus 1's on the diagonal above the main diagonal, and then we're going to have minus 1's on the diagonal below the diagonal, and 0's everywhere else. This is an n minus 1 by n minus 1 matrix. So let me put n minus 1 rows here and n minus 1 columns here. Now, in general, like I said, n could be very large. N could be very large. Imagine it's 10,000. That's a pretty fine grid, but imagine n is equal to 10,000 in this case. It's going to be basically a 10,000 by 10,000 matrix, so it's going to be huge. So an algorithm like just straight up Gaussian elimination is going to take way too long to run on something like this. Now, an advantage of this matrix, there's two main structures, aside from the tridiagonal, which I'll get to in just a minute, there are two main structural features of this matrix. One, almost all of the entries are 0. Okay, this was a problem that you were asked to do on the week 1 homework. Almost all of the entries are 0, and it is a symmetric matrix. Okay, because of that, what we can do is we can use iterative methods. Instead of solving this directly, we can use an iterative method. Now, the reason that we can use an iterative method is because an iterative method requires doing doing a whole bunch of matrix vector operations. And if you have a matrix where many of the entries are 0, there are specialized algorithms that will allow you to do these matrix vector products very quickly, much more quickly than the typical n squared number of steps that you need to take. On the other hand, this is a tridiagonal matrix, and there are even better solvers for tridiagonal matrices that can solve this in roughly n steps, or a time that's proportional to n here, rather than n squared or n cubed or something like that. For example, the Thomas algorithm is one of these. So practically speaking, we would never use an iterative method to solve a matrix like to solve a matrix vector equation where this is the matrix. Now, when we look in the next videos in the Poisson's equation for a square, we're no longer going to have a tridiagonal matrix, and then it is much more appropriate to use iterative methods. Okay, so again, what we're doing here is we have converted our differential equation to a system of linear equations, and we can use linear algebra stuff to solve that system of linear equations. One of the tools that we're learning in this class, or the main tool that we're learning in this class to solve large sparse systems like this, sparse meaning there's a high percentage of zero entries. One of the tools we're learning to solve sparse systems like this is iterative methods. That is one of the things that's in our that will be in our linear algebra toolbox. But it just doesn't exactly apply to this precise matrix, but it will when we look at matrices for problems that are from higher dimensions. But we can still apply the iterative methods to this matrix. It just isn't something that necessarily makes a whole lot of sense. Okay, so that is it for this video, the sort of discretization of the Poisson's equation on one dimension. And in upcoming videos, I'll show you how we can do this for Poisson's equation on the disk, or on the square.